When you step into the extraordinary realm of physics, you quickly realize that the world is filled with substances and materials that behave in ways that seem to challenge our conventional understanding of nature. Some of these materials occur naturally, shaped over eons by geological and cosmic processes. Others are painstakingly engineered in laboratories, born from human curiosity and the desire to push the boundaries of what's possible. From metallic substances reminiscent of the Terminator films to substances so strong they may be unrivaled anywhere in the known universe, each of these fascinating materials appears to defy the very laws of physics as we know them. Ferrofluid, a magnetic marvel. Consider ferrofluid. Its very name is a combination of the words ferro, referring to iron-based ferromagnets, and fluid. A ferrofluid is a liquid that becomes magnetized in the presence of a magnetic field. It is typically composed of tiny ferromagnetic particles, each coated with a surfactant to keep them from clumping together, then suspended in a carrier fluid like an organic solvent or water. When exposed to a strong magnet, a ferrofluid's smooth surface erupts into a mesmerizing array of metallic spikes. These spikes seem to dance and shift in response to the invisible lines of magnetic force. The fluid's remarkable ability to adopt complex patterns results from the interplay of several factors: the magnetic force on the ferrous particles, the effect of gravity, and the surface tension of the fluid's outer layer. This interplay gives rise to a distinctive, otherworldly display, one that has found applications in everything from loudspeaker dampening to innovative art installations. Sulfur hexafluoride, SF6, a dense and enigmatic gas, moving from mesmerizing liquids to unusual gases. Sulfur hexafluoride, SF6, is a heavy, inert, and non-toxic compound. Often used as an insulating medium in high-voltage electrical systems, SF6 excels at preventing electrical arcs. Completely colorless and significantly denser than air, about 5 times as heavy, it can be poured from a container almost like water. This density enables intriguing demonstrations. Place a container filled with SF6 on a table, and you can float lightweight objects on it as if they were resting atop a pool of invisible liquid. Inhale a small amount with proper safety measures, and your voice drops dramatically in pitch, the opposite effect of helium. Yet, behind these entertaining properties lies a serious environmental drawback. SF6 is one of the most potent greenhouse gases known, with a global warming potential tens of thousands of times greater than carbon dioxide. Its industrial benefits come at the cost of a significant environmental responsibility. Rubidium, a metal with a fiery temper. Rubidium is a soft, silvery white metal that ranks as the 25th most abundant element in the Earth's crust. Despite its relative prevalence, it's not as commonly encountered as more familiar metals. What makes rubidium truly stand out is its intense reactivity. Solid at room temperature, rubidium has a low melting point of just over 100 degrees, about 39 degrees. Place it in contact with water, and it reacts violently, releasing hydrogen gas that ignites, producing a burst of flame and heat. Its readiness to oxidize even in moist air makes it a metal that must be stored with great care. Fascinatingly, rubidium salts have uses in glass and ceramic manufacturing, and they can create vibrant purples in fireworks. In the future, rubidium's ease of ionization might make it an attractive candidate for advanced propulsion systems in spacecraft, hinting at more peaceful, constructive uses for this otherwise fiery element. Gallium, the Terminator, metal that melts in your hand. If you've ever seen the shape-shifting T-1000 robot in the Terminator franchise, gallium might come to mind. This metal is soft and silvery blue at room temperature, but hold it in your hand and watch as your body heat gently liquefies it. Known for its remarkable low melting point, a mere 85.6 degrees bars or 29.8 degrees Celsius, gallium seems almost alive as it flows and drips. It's commonly used in high-speed electronic circuits, as well as in LEDs and laser diodes that emit blue and violet light. When gallium is mixed with certain chemicals, like hydrogen peroxide, it behaves even more dramatically, sometimes appearing to move and change shape on its own. It can also corrode aluminum, gnawing through it in surprising ways. As if that weren't enough, gallium's antibacterial properties are being studied for potential medical applications, including treating infections and certain types of cancer. Its combination of scientific value, commercial utility, and bizarre behavior ensures gallium remains a material of enduring fascination. Smart textiles and wearable technologies, clothing of the future. As technology continues to integrate seamlessly into our daily lives, the world of textiles is undergoing a quiet revolution. Smart fabrics, also known as e-textiles or wearable technologies, do far more than provide warmth or protection. They can harness ambient energy from heat, sound, or vibrations, and convert these into usable power. Some advanced fabrics even respond to changes in the wearer's body temperature or environment, adjusting their properties in real time. Imagine clothes that light up when you receive a text message, or fabrics that stiffen upon impact, providing immediate protection to the wearer. Designers like Yingao have created garments that integrate photoluminescent threads and eye-tracking technology. When a viewer gazes upon these dresses, they seem to come alive, shifting patterns and glowing softly, an uncanny melding of fashion, art, and engineering. Beyond aesthetics, these materials hold promise in fields such as healthcare, military defense, and space exploration, where protective suits must endure extreme conditions. Self-healing polymers, materials that mend themselves. What if broken objects could heal like living organisms? Enter self-healing polymers. Researchers have developed catalyst-based materials that form long-chain polymers capable of reassembling when cut. By carefully designing polymer chains with special molecular architectures and using a rare metal catalyst, like scandium, these materials can recognize when they've been severed and spontaneously fuse back together. Even more impressive is that many can repair themselves in both dry and wet conditions without external energy, heat, or light. Imagine the implications. A cracked phone screen that seals itself overnight, structural components in airplanes or cars that mend after minor damage, or medical implants that adapt and heal internally. Such breakthroughs could significantly reduce waste, enhance safety, and prolong the lifespan of countless products. Nitinol nickel titanium alloy, the metal with a memory. Nitinol, an alloy composed of roughly equal parts nickel and titanium, is best known for its shape memory effect. Bend it at a lower temperature, and it will hold that altered shape, until you warm it slightly, at which point it returns to its original form as if remembering its true state. This remarkable behavior is due to a reversible solid-state phase transformation known as a martensitic transformation. At higher temperatures, nitinol's crystal structure, austenite, is stable, and at lower temperatures, it shifts to a more complex structure, martensite. The implications are vast. Nitinol can be used in eyeglass frames that snap back into shape, medical stents that adapt to the body's anatomy, and even actuators in aerospace applications. It's a prime example of how adjusting an element's microscopic structure can yield remarkable macroscopic properties. Starlight, a mystery material beyond imagination. Some materials remain shrouded in enigma, none more so than starlight. Allegedly invented by the late British hairdresser and amateur chemist Maurice Ward, starlight gained fame for its astonishing ability to withstand extreme heat. In military tests, it reportedly protected objects, like raw eggs, from temperatures similar to those generated by a nuclear blast. After exposure to intense heat, an egg coated with starlight could still be cracked open, raw and unscathed. While the exact composition of starlight was a closely guarded secret, this wonder material stands as a symbol of unexplored frontiers in material science, promising that we have only begun to scratch the surface of what is possible. Aerogel, frozen smoke and miracle insulator. Born from a bet between two scientists in the early 1930s, aerogel is a substance that seems like it belongs on a distant planet. Created by removing the liquid from a gel extremely slowly, leaving only a delicate lattice of solid behind, aerogel is composed mostly of air. Its ghostly, translucent appearance has earned it nicknames like frozen smoke or blue air. Aerogels are extraordinarily light and have some of the lowest thermal conductivities of any known solid, making them phenomenal insulators. You can hold a flame beneath an aerogel block and barely feel warmth on the other side. From protecting spacecraft instruments against intense heat during atmospheric re-entry to insulating sensitive electronics and even keeping delicate flowers from scorching under a torch, aerogel demonstrates that the line between solid, liquid, and gas can be artfully blurred. Graphene. The ultimate material? Graphene, a single layer of carbon atoms arranged in a two-dimensional hexagonal lattice, may well be the star of modern materials science. Stronger than steel by orders of magnitude, yet incredibly lightweight, graphene is also nearly transparent and conducts electricity and heat with astonishing efficiency. Its discovery earned its researchers a Nobel Prize in physics, and since then, a flurry of research has sought ways to integrate graphene into countless applications. Flexible electronics, ultra-sensitive sensors, enhanced composites, and faster computer chips are just the beginning. As researchers learn to mass-produce graphene affordably, its influence may reshape entire industries, offering performance improvements and eco-friendly alternatives to traditional materials. Charting the future of advanced materials. From magnet-responsive liquids and shape-shifting metals to self-healing polymers and ultra-strong carbon sheets, these materials don't just challenge our understanding of physics, they expand it. They invite us to reconsider what is possible and push forward the frontiers of engineering, technology, and art. Which of these remarkable substances captivates you the most? Perhaps it's the mesmerizing spikes of ferrofluid, the uncanny softness of gallium melting in your palm, or the near indestructible strength of graphene. As material science progresses, these once mysterious substances may soon become part of our everyday lives, improving safety, comfort, and sustainability in countless ways. If you found this exploration of physics-defying materials intriguing, let us know which one fascinated you the most. And if you enjoyed this deep dive, consider subscribing to stay updated on the latest discoveries and innovations. The future of materials is unfolding now, and it's more astonishing than ever.